Number 15. Here we have a polynomial x to the 4 plus x to the 3 plus x squared plus x plus 1. Now we want to write this polynomial as the difference of the square of two polynomials. So here the requirement is both polynomials ux and vx, their coefficients are all real numbers, and the coefficient of the leading term is positive, and also the degree are different. Obviously, the degree of u should be bigger than the degree of v. All right. Okay, so based on this, it's clear the degree of ux has to be 2, because when you take, so that when you take the square, you get the x to the 4. And then if you look at the vx, the degree of vx at the most is 1. It could happen, it's just a constant term, but we cannot rule that out at the first place. All right, so precise speaking, solution. I should have the ux. The first term is x squared, because when you take the square, you should get the x to the 4, and the coefficient is 1. And plus this ax, and plus the b, okay? And I have this vx is cx and plus d. And because here we require the leading coefficient to be positive, well, here I more precisely we should say non-negative. We can rule out later. It just cannot be 0. All right. Okay. Now I want this px equals x squared plus ax plus b squared minus cx plus the d squared. Right. If we look at the x cube, because x cube can only come from this part, not this part. So from this, I quickly get the a has to be 1/2. In order, when you write out, you get the term x cubed with coefficient 1. So from here, I can rewrite everything as, I'll get x to the 4 plus x to the 3 plus x2 plus x plus 1 equals x squared plus x over 2 plus b squared and minus cx plus d squared. Okay. Based on this setup, the next we need to do, we just write out and compare coefficients of different power of x, and then we set up equations. Here we have 3 unknowns, b, c, d. So we expect to have 3 equations. Okay. All right. So based on, so from here I get, if I base it on the square, let me write this one out. So this is just the x to the 4 plus x to the cube, and then plus 2b plus 104 times x squared, right? And then I have, this is the bx, the x term, and then I plus the b squared minus, this is c squared x squared minus 2cd x, and then minus d squared. Let me combine like terms. We have x to the 4 plus x cubed, and plus this is 2b plus 104 minus cx x squared, and then plus b minus 2cd and x, and plus b squared minus d squared. Okay, so these 2 terms, they are already coincide, so we don't need to worry. Let's just compare the term of x squared to the x squared, and we have x to the x, and then of course we also have this a constant term, which is b squared minus d squared. Okay, so based on coefficients of the 3 terms, we'll have equations. So we get 3 equations. Number 1, we have it's 2b plus 104 minus c squared. This one equals 1. So this is the first one. And then we have the second one is b minus 2cd. This is also 1. And the last one is b squared minus d squared. This is also 1. Okay, so we have 3 equations, and we have 3 unknowns. The question is, we need to solve it. Right? The problem is how many different solutions we have. Okay, now how should we approach this equation? Obviously, if I rewrite the whole thing, I can write this is 2b is c squared plus 304 and this is b equals 1 plus 2cd, and this is b squared equals 1 plus d squared. Now, usually, if you have three equations or two equations with three unknowns or two unknowns, the common strategy is try to get rid of variables, right, by elimination. You can choose whatever you feel works better for you to eliminate. So here I will go with here, because this I have b and this is b squared. For this two I combine to get, let's solve this. So I will have 1 plus d squared equals 1 plus 2cd squared, right? Okay, so let me write this one out. So this implies 1 plus d squared equals, my point is, the whole problem is to reduce to solve this algebraic system of equations, right? It's non-linear because you have those square terms, right? But it's okay, it's not too hard. So we take the square on both sides, we get 1 plus 4cd and plus 4 squared d squared. We just need more patience and make sure, you can double check, make sure we algebraic operations are correct. Otherwise, we will get something which is something that is wrong. Okay, just be careful and be patient. Now I have 1, 1 cancel with 1, 1. Okay, so then this is what I have, right? Now, because I have this common d, 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 we need to look at two cases. Case 1 is d is 0. Case 2 is d is not 0. If d is not 0, then we can just cancel d on both sides. So I look at case 1. Case 1, if d is 0, then this is automatically true. Then I have my b will just be 1, right? And my c is, you can just calculate the c will be square root 5 over 2. Okay, now this is definitely is a valid solution. For this case, we just have the x4 plus x3 plus x2 plus x plus 1. This equals x squared plus x over 2 and plus 1 squared minus square 5 over 2 times x times square, right? So this is my ux, this is my ux, this is my vx, right? So here we get, for this case, we get one solution, right? One solution. Possible u and v. The question is whether this is the only one. Well, in order to see whether we have more solutions, let's look at the case 2, d is not 0. Okay? So I look at, let me use different colors. So I have to look at the case 2, d is not 0. Now, if d is not 0, so from here, I can get what I have. I can divide d on both sides, so I get d equals 4c plus 4c squared times d, right? Okay, so from here, I can get my d. I can solve the d is 4c, 1 minus 4c squared. Now, clearly, this one cannot be 0. Otherwise, it's not going to satisfy this equality. All right, so this is what I have. Okay, so what's the next? The next is I'm going to put this back into these two equations, right? I'm going to set up the equation for C, okay? Because, let me try to solve it. Since I have 2b plus c squared plus equals, right? So I have the 2b, this two, maybe let me just put it here. Based on this two, I will get c squared plus 3 over 4 equals the twice of 1 plus 2cd, which is 2 plus 4cd, right? Okay, so then I can just plug this c, this d, replace the d by the expression I get here, and this will give me an equation of c. Okay, this looks a bit tedious, but it's doable, so let's do it. So after I do that, I will get equation is c squared equals 5 over 4. We just need to make sure our calculations are correct. I need to be a bit careful. All right, so I get a 16 c squared over 1 minus 4c squared. Okay, so now we need to simplify this expression. Let's multiply 4 and 1 minus 4 squared on both sides to get rid of the fraction terms. All right, so we get it's 4 times 1 minus 4c squared. Will times c squared equals 5 times 1 minus 4c squared plus 64c squared. Okay, so let's be a bit patient and careful. So let's calculate this out. So we get 4c squared minus 16c cubed equals 5 minus 20c squared plus 64c squared, right? Okay, let's combine those terms. So here I have this c squared, and then I have c to the 4 and a square, and then I have a constant, right? Okay, so after simplification, we get 16c4 and plus 40c squared. Yes, let's see, it's correct. Okay, so plus 5 equals 0. All right, so you see, so this one could write a c squared. So this is a quadratic equation for c squared. Now you just apply the quadratic formula, you'll quickly realize, so this by, either you can say by quadratic formula or by Vieta formula. Either way, so by a quadratic formula, you'll get a c squared is negative, which is impossible. Okay, so as a conclusion, we derive case 2. Case 2, that's the case 2. This is impossible. So this one is impossible. Right? So we go back to what we have here, and we conclude this one, the case 1. This is the only valid case. This is the only valid case. We are done. Okay, now here the point for this problem is, according to assumption, we quickly derive the degree of u has to be 2, the degree of v is at most 1. So we set up a quadratic equation and first order linear polynomial. Okay, so then we just write out and compare the coefficients. Now the key, those things are kind of straightforward and routine. Now the main, I would say the main difficulty is how you handle this equation. So here we have 3 equations that involve square terms and 3 unknowns B, C, D. The general strategy to deal system equations is always like, I try to find a nice way to eliminate variables. So here you can do whatever that works for you. So what I did is I first eliminate the variable b. Right? I first do for the last 2, and then I do for the first 2. Okay. Problem number 16. Here we have an equation that involves a square root, and we need to figure out for what kind of p this one has a solution, especially what's the largest possible value of p. This is past the IMO problem. It was the first problem in the day 1 of 1 year's IMO. The problem is not terribly hard. What we need to do is just be patient and do some algebraic calculations. Okay, so number 1, whenever you see a square root, the usual strategy is to take square on both sides in order to remove the square root, right? So let's implement that strategy solution. I'm going to take a square. Okay, first let's move one to the other side. I choose to move this to the other side so that because the other one has 2, which is more convenient to be squared individually. So I have 2, the square root of x squared minus 1 equals x minus the square root of x squared minus b. First of all, if you look at the equation, you quickly get x has to be non-negative, right? Okay. So let's take the square on both sides. From here, I take the square. So I take the square on both sides, right? All right, so this gives me 4 times x squared minus 1 equals x squared minus 2x times the square root of x squared minus p and plus x squared minus p. Okay, now we have this is x squared, px, those terms that does not have a square root. Let's move them to one side, and here we have another square root. All right, so let's move the others to the left-hand side, and then we take square root, take square again, right? Okay, so let's do it. So here we have, I combine those like terms, I'll get 2x squared minus plus the p minus 4, right? Equals negative 2x the square root of x squared minus p. Okay, now let me take the square root again. So take the square. So this implies I take the square on both sides. Let me write one more step. So 2x squared plus p minus 4 squared equals 4x squared times x squared minus p. Now, when you reach at this step, you might think this is horrible because I'm going to get the 4 power. But the thing is, you see quickly the 4 power just be canceled. Okay, so let's see. Okay, so let's write out. So here is 4x to the 4 plus 4x squared times p minus 4, right? And then plus p minus 4 squared equals 4x to the 4 and minus 4x to the power p. Okay, great. So we quickly see these two things, they are cancelled with each other. Now I move this x to the other side, and then I move those constant to the other side. Okay, to the right-hand side. So from here, what we let's see what we have. So we get 4x squared, right? Okay, so 2p minus 4 equals negative p minus 4 squared. Okay, so from here you see, because this one is less than 0, this is bigger than 0. If I have, so let's look, if I number 1, if I have p is 4, right? If p is 4, then I get the x is 0, but this is not valid. This is not valid, since x squared minus 1 will become negative, which is cannot take a square root, right? Okay, all right. So this is not valid, because if we look at this one again, so from this one tells us the x squared, this one has to be bigger or equivalent to 1, right? Okay, so this is so we get rid of this. Now, then we must have the p. So p, of course, p cannot be 2. Otherwise, the left-hand side will be 0 and the otherwise not. So combine this, I must have the p has to be less than 2. So I get the expression, I get 4x squared equals p minus 4 squared and divided by 4 minus 2p, all right? And this gives me the x, because I also know the x since x is bigger than 0, and this quickly gives me the x squared. Oh, oops. I have the x squared equals 4 times 4 minus 2p, and this is p minus 4 squared, right? I take the square root. So take the square root, I get x is 4 minus p to the square root of 4 minus 2p. Okay, now my point is, like, after we keep taking the square roots and we analyze the positive or negative, then we get, if it has a solution, the solution has to be expressed as 4 minus p divided by 2 times the square root of 4 minus 2p. When you look at this, you may say, oh, this is solved because I get the explicit formula of the solution, and the p is just be less than 2. Well, there's a subtle issue here. The subtle issue is, when we solve this one, what we did is we keep taking a square. So here's the subtle issue. So the subtle issue is, if a equals b implies a squared equals b squared, right? That's no question. Nevertheless, a squared equals b squared does not, usually you cannot go back to derive that a equals b. That's not necessarily true, because you can also have since you can also have a is b, this is also all right. Okay, so that means we have to be careful to check this one is indeed the solution. So the point is this point. Maybe I put red. We need to check. Let's say this is put star. Star is indeed a solution. Okay. All right, so check means we just put it back into the expression. Okay, so let me move here. So let's recall the equation. So the equation is the square root of x squared minus p plus the square root of x squared minus 1 equals x. Now we already know the p has first restriction on p. The p has to be less than 2. And also since the x is bigger or equivalent to x squared minus p, we also have the p has to be bigger or equal to 0, right? Since, here. Okay, so I get the first restriction p has to be non-negative and also less than 2. Now, I'm going to plug this into the equation. Let's do it. Okay. Again, just be patient and make sure our calculations are correct. All right, so we have the x squared equals, we just did. So 4 minus p squared, and this is 4 minus 2p. So from here, I get the x squared minus p, what I have. So this is 4 times 4 minus 2p, right? We have 4 minus p squared minus 4p times 4 minus 2p. So if we write out, this will be 16 minus 8p plus p squared minus 16p plus 8p squared. Okay, so if I combine this, what I get? I get is 9p squared minus 24p and plus 16, right? Okay, what is this? This is 3p minus 4 squared. Okay, so summarize. So from here, I just derive x squared minus p equals 4 times 4 minus 2p, 3p minus 4 squared. So that's what I have. Okay, good. All right, so that's this is the first one. So if I take the square root, and this tells me, if I take the square root, I take the square root of x squared minus p, so that's what I have here. This one equals the absolute value of 3p minus 4. Here is 2, the square root of 4 minus 2p. The reason we need to take the square root is because I don't know whether it's positive or negative, right? You take the square root of something square, which is, if we don't know it's positive or negative, we need to take the absolute value, right? So this is because the square root of a squared equals the absolute value of a. Okay. Then let's calculate this one. So let's calculate, oops, x squared minus 1. So that's what we have. So we just repeat the calculation. So 4 minus p squared, 4 times 4 minus 2p minus 1. So that's 4 minus 2p, 16 minus 8p plus p squared minus 16 plus 8p, right? Okay. This one is more convenient because we just cancel with each other. All right, so I get this is the p squared divided by 4 times 4 minus 2p. Okay, so from here I get, so I get by this, let me just read. So x squared minus 1, I get this is p squared, 4 minus 2p. Since we already have the p is non-negative and between 0 and 2, right? So since we have this, so I get the square root of x squared minus 1. This is p over 2 times the square root of 4 minus 2p. Okay, good. All right. So here we get the square root of x squared minus p. We also get the square root of x squared minus 1. And let's recall, we also have the x here, right? So we have the x here. So this we already get x. So let me put it here. So just collect all the pieces of information we get so far. So I have the x, my x is, let me put, okay, so it's 4 minus p, this 2 the square root of 4 minus 2p. Now let's go back to our equation. Oh, there should be 2 here, I forgot 2 here. Okay, so there's 2 here. Let's go back to our equation. So that's the equation. So let's put the equation. The equation is the square root of, let's recall, so square root of x squared minus p plus the square root of x squared minus 1. This is x. Okay, so I just put all those expressions into where they should be, right? Okay, so then there's 2. I always forget there's 2. There's 2 here. Okay, so 2 here. All right, so then I have 3p minus 4 times over the square root of 4 minus 2p and plus this is 2 times, this is p, right? And 2 the square root of 4 minus 2p, and this is 4 minus p, 2 times the square root of 2 minus 2p. Okay, right? So this is what we have. Okay, good. Now we can just cancel, cancel, cancel. And finally, this gives me the absolute value of 3p minus 4, right? Plus 2p equals 4 minus p. Okay, so it's the absolute value of 3p minus 4 equals 4 minus 3p, right? Okay, now you see, in order for this to be true, because this is the absolute value, 3p minus 4, 4 minus 3p, and this one has to be non-negative, should be bigger or equivalent to 0. Maybe I use the right ones. This should be bigger or equivalent to 0. All right, so this is, they're just opposite to each other. So from here, what do I need to do? I just need 4 minus 3p. This is non-negative. And this tells me that p should be less or equal to 4 over 3. Okay, so as a conclusion, when p is less or equivalent to 3 or 4, and meanwhile, they should be bigger or equal to 0, bigger or equal to 0, the equation x squared of x squared minus 1 plus, oops, let me rewrite it. I keep forgetting the 2 for some reason. Plus 2, the square root of x squared minus 1 equals x. This one has solution, or I say solutions. All right, so that the largest p possible is 4 over 3. Problem number 17. This is a problem about complex numbers combined with a quadratic equation. Okay, so this problem is from the Chinese high school math computation in 1994. That was the year that I participated in the math computation, the high school math computation. It was 26 years ago. When I look at this problem, I couldn't recognize it all. But anyway, so here, what we know is Z1, Z2 are coefficients, right? Z1 is coefficient of x, and Z2 plus m is the constant term. Alpha, beta are 2 roots of this quadratic equation. Now, what do we know is the magnitude of alpha minus beta is 2 times the square root 7, and plus some information about Z1 and Z2. Okay, so when you look at roots, it's kind of clear. Usually, we should try to use the Vieta formula to connect the roots with coefficients. Here are Z1 and Z2. Now, here what we have is alpha minus beta. When we apply the Vieta formula, usually it's alpha times beta and alpha plus beta. So how should we connect alpha minus beta with alpha plus beta and alpha times beta? The usual trick is we take the square. Okay, so solution. We are going to apply, so the trick is we are going to use the Vieta formula. We have this alpha minus beta squared. This equals alpha squared plus beta squared minus 2 alpha beta, right? Now I can rewrite this as alpha plus beta squared and minus 4 times alpha beta. Okay, then I can just apply the Vieta formula. So alpha plus beta, so this is the Z1 squared. Alpha times beta, this is Z2 plus n. All right, so this is just minus 4 times Z2 plus n. Okay, then I take the magnitude on both sides. So from here, we derive the magnitude of alpha minus beta squared equals magnitude of Z1 squared minus 4 Z2 plus n, right? Okay, and this equals Z1 squared minus 4Z2 minus 4n. Now, we already know Z1 squared minus 4Z2 is given by a fixed complex number. So this one equals 16 plus 20i. Okay, how about this one? Well, this one is just, if we recall some basic property about magnitude, we have the magnitude of Z squared equals the square of the magnitude. So this is identity in complex number. So based on that, we quickly get this one equals the alpha minus beta mesh squared, and this is what we know is 28. Okay, then this gives us an identity. We get 28 equals the magnitude of 16 plus 20i minus 4n. Okay, so clearly we can define, we can divide 4 on both sides to further simplify the equation. Here we have 7 equals 4 plus 5i minus n. Now, if you look at this magnitude, this expression, this one just represents the distance from the n to this fixed number, this fixed complex number, the distance 7. If we collect all such n, it's a circle. So I have, this implies the n, if I draw the complex plane, okay, this is the point 4 and 5, so this is 4. Let's say this is 5. So this is 4 plus 5i. Okay, so now we have the circle stand at this point with radius 7. So the radius is 7. The n will be just on the circle. So this is the collection of all possible n. And this is what it tells us, right? Okay. Now, what we need to find? We need to find is the largest possible value of the magnitude of n. If you look at geometrically, when you look at this, clearly the largest one shall be go if you just go with connect the origin with the center and you extend it, and this is the n. This is with the largest. This is give the largest magnitude of n. Right? For other, it's very easy to see because if you look at other n, if you connect the n, oh, maybe I use different color. So if you connect n, so if I connect the other n, when you compare this is 7, right? So obviously this will be less than the 7 plus that. So this one equals the 7 plus the magnitude of 4 plus 5i, right? So for the other, if you from the big picture, you see it's always less or equivalent to this number, just because if you have a triangle, one side is always less than the sum of the other two sides, right? That's clear. All right, okay, so now we calculate this. This is the square root of 16 plus 25. That's the square root of 41. So I get the answer, the largest n equals 7 plus this. So that's 7 plus, so 7 right here. And the other one is right here. So this is the square root of 41. Okay, so 7 plus the square root of 41. So the answer is 48, right? So this is my A, and this is my B. Okay, all right. So here, the main point we use, the main ingredients we use is number 1. The key thing I will say, the key point is this one. We try to express alpha minus beta in terms of the other formula. Then we just plug those given information into this expression. We'll get the n. All those that n are along the circle, the center at the point 4 plus 5i with radius 7. Then geometrically, we can quickly figure out the largest one. Problem number 18. Here we have a special regular polygon with a relation between side length, that's 1 over AB, equals 1 over AC plus 1 over AD. Now, based on this piece of information, we need to determine the number of sides of this polygon. Okay, I don't know how to solve this one using a pure geometric method. Maybe there's one, okay. But anyway, what I did is I use trigonometric functions. That's one of approaches to attack geometry problem. I remember when I participated in the high school math competition, as I mentioned, that was in 1994. The second part, Chinese high school math competition has 2 parts. The first part is like AMC or kind of AMI, that's multiple choice plus fill in blank problems. The second part is some computation plus proof problem. So this is that's like a JMO or AMO part. I remember I proved for the geometry problem, the second one. It's a proof problem. What I did is I proved the problem. I just use a pure trigonometric ways. Well, basically I translate all those geometric relations into algebraic relations involving trigonometric functions. Then I just need to prove some identities of trigonometric functions are correct. All right, so here I'm going to use the same approach. That means I'm going to express those things A, B, A, C, A, D using trigonometric functions. Then everything is reduced to algebraic calculations based on trigonometric functions. Now, one thing, if you want to use trigonometric functions to solve geometry problem, one thing you need to be familiar with is those trigonometric identities, especially how you handle those sum and product formulas. Okay, we'll see, or double angle formulas. Okay. Now, say I put this angle as theta, right? So I introduce the angle theta. Equivalently, we can put this polygon in a circle with radius 1. And then I have the angle theta right here. So this will be 2 theta. This will be 2 theta. And this is also 2 theta. So as I said, I'm going to express those side lengths using trigonometric functions of theta. So first, let's recall a basic fact. Suppose I have an isosceles triangle. And this is 1, this is 1. This angle is 2a. Now, if I bisect this angle, equivalently, it's the height to the other side, right? So then this is a, this is a. I get this side is just sine a, and this side is, this part is also sine a. So combined, this is twice of sine a. Okay, based on that, we'll get, from this, we'll get this AB equals sine theta, and AC equals sine 2 theta, and I have this AD equals sine 3 theta. All right, then I can reduce this relation, can be written in terms of trigonometric functions. So it's 1 over sine theta equals 1 over sine 2 theta plus 1 over sine 3 theta. Now this theta, of course, is just pi over the n, right? So n is the number of sides, which is bigger than 1 but less than pi over 2, right? Okay. All right. Now what we need to do is we need to simplify. Basically, we just need to solve this trigonometric equation. So first, let's simplify it. You have those fractions, right? So we multiply those common denominators on both sides and to remove those fractions, right? So from here, we can get sine 2 theta, sine 3 theta equals sine theta, sine 3 theta plus sine theta and sine 2 theta, right? So this is what we have. Okay, now we have this equation. All right, now let's recall the the double angle formula. So this one I can written as 2 sine theta times cosine theta, right? So that's the double angle formula. The point is, I have sine theta here, and sine theta here. I can cancel sine theta on both sides because theta is not pi, it's not 0, right? So it's sine theta is not 0, I cancel it. So therefore, I get this twice sine 3 theta cosine theta equals sine 3 theta plus sine 2 theta. The question is, what's next? Okay, now look at 2 times sine theta times cosine theta. Now, if you're familiar with those trigonometric identities, you say, oh, now I can write this as the sum of 2 trigonometric functions. Now, let's recall the formula. So here we are going to use, let's recall trigonometric identity. that this thing we have a sine alpha times 2 cosine alpha times cosine beta equals sine alpha plus beta plus sine alpha minus beta. We have this trigonometric identity. All right. Okay. Well, it's not easy to memorize all trigonometric identities. In fact, you just need to memorize one. That's the central one. Everything else can be deduced from that. So let me put this in the so I call central trig identity. Is this sine alpha plus beta equals sine alpha times cosine beta plus cosine alpha times sine beta. Just memorize this. All the others can be deduced from here. Because if you change this to alpha minus beta, right? So you just change this to minus beta. We change this to minus beta, and then it's okay. Sine, cosine minus beta is cosine beta, sine minus beta, next sine beta. And you quickly will get this, okay, this is sine alpha times cosine beta minus cosine alpha times sine beta, right? You can also get cosine because you can go from sine to cosine, just pi over 2 minus that. Now, if you add this together, in particular, if you add these two together, right, like here. So if you add them together, and together, this will cancel with each other. So you quickly get what we have here. Okay, that's my point. So this is what I'm trying to say is this one is the central trig identity. Anything else can be deduced from this. Okay, now, all right, so we have is okay, I have this one. I'm going to apply this right to here. That's what we want. Okay? Now, from then this one will be sine 4 theta plus sine 2 theta equals sine 3 theta plus sine 2 theta. Then you quickly realize sine 2 theta, they cancel with each other. Well, in fact, if you're very familiar with those trigonometric identities, then you know when you see 2 theta here, when you see 3 theta to 2 theta, you should quickly realize, oh, then I should write this as the sum of sine because I quickly get sine 2 theta, right? Okay. All right. Then from here, I just deduce what I have. I deduce the sine 4 theta equals sine 4 theta equals sine 3 theta. Great. Now we can claim victory because if I have the sine, let's recall, if I have sine A equals sine B, I have two possibilities, right? Either this implies, because here, all those angles, I have either A plus B equals 2k plus 1 times pi, right? Or I have, say, A is B plus 2k pi, right? 2k and pi. Now, given the range, let's recall the range of our theta is right here. So this is the range of our theta, which is between 0 and pi over 2, right? So since our theta is between 0 and pi over 2, right? Pi over 2. Okay, so the only possibility we have is 4 theta plus 3 theta equals pi, right? So that's the only thing that's going to make it work. So from here, I deduce my theta is pi over 7. Okay, so accordingly, the n is 7. The n is 7. Okay, now for this problem, if we quickly go over it, we have, okay, so the trick we use is we use trigonometric functions to represent the length of sides, and then everything is reduced to compute trigonometric functions. This is a very nice approach, especially for those people who like algebra and feel comfortable to play around trigonometric functions. Like say you're weak in geometry. What weak means it's not as strong as the algebra. Then you say, okay, I can change the geometric relation into algebra relation. And I just go around play around those algebraic identities. Like here, we use is trigonometric identities, right? So first we use the double angle formula. So that's the first thing we use. And then we use the relation between sum and the product, and combine the two pieces together. We quickly get here sine 4 theta equals sine 4 theta equals sine 3 theta. And this implies theta is pi over. Okay. Problem number 19. Here we have a circular cone, and we have 2 points A and B on the circular cone. Okay, so the point is we go around twice from A to B, and the question is basically asking what is the shortest distance to go from A to B. For this kind of problem, the general strategy is to expand this cone from a 3-dimensional picture to a 2-dimensional picture. Okay, and then we'll quickly see what shall be the shortest path. Now, the only thing here we need to be a bit careful because the curve goes around twice. So when we expand it, we need to expand twice. Okay, so we can separate this curve into 2 parts, right? The first part is go once. This is the first part. And then we can look at the second part, right? Okay, now if I expand, if I expand once, let's see. Here I have a cone, circular cone. The diameter is 1, so the radius is 1/2, and we have the center height is 3. So if I expand this one just once, what I get, this is what I get, right? Okay, so this is 3. The length, which is the parameter of the base circle, so it's right here. This one is pi, right? This is pi. Okay, because here the parameter is pi. All right, so we have this angle. We get this angle will be 60 degrees. So I have this is pi over 3, or I just write as 60 degree, right? So as I said, because the curve goes around twice, so we need to expand the cone twice. Okay, let's do it. We expand once, and then we expand second time. So A is in the middle, and this is B. Okay, so here we have 60 degrees, here we have 6 degrees. So this is 3/2. This is the whole, the radius, the whole radius is 3. All right, so in general, if I have a curve, let's forget about the shortest one, right? If I have a curve start from A and go around twice, go to B, what we are going to have is things like this, right? So you first go from A, okay, to this point once, and then you have the second, go from this to the B. So clearly, if I want to get the shortest path, we should strictly go from A to B, right? So I should strictly go from A to B. This is the shortest path. All right. So our D will be, so first from here to this, so this is just the point D. Okay, so and the second, this is the green part, right? From D to B. Okay, so we just need to figure out what is AB. For that, since we have this triangle, this is, here we have this triangle. So this 3/2, this is 3, and here we have this is 120 degrees. We can just apply the law of cosine. So we're gonna apply law of cosine. So by law of cosine, we have the AB squared equals 3/2 squared, right? Plus 3 squared minus 2 times 3/2 times 3 and times cosine 120 degree. Okay, so for cosine 120 degree, this one equals negative 1/2, right? Negative 1/2. Okay, and then we have this equals, we have this equals 9/4 plus 9 and plus this is 9/2. This gives us is 9. 1/4 plus 1 plus 1/2. If you combine these 3 fractions together, we get is 7/4, right? So, okay, so it's 9 times 7/4. Okay, so then I have AB squared. So I have AB squared equals 904 times 7. So if I take the square root on both sides, I get 3/2 times the square root of 7. Right? Okay, so we get the shortest path from A to B. And if we fold this one back, to the cone, we also figure out what shall be the shortest path, right? Shortest distance and shortest path. Okay, we have done similar problems, I think, in the first exercise. If we have a rectangle box, right? If you go from one point to another point, what you do is, again, similar. You just unfold it from a 3D picture to a 2D picture. Because from 2D picture, we know from one point to another is the shortest line. So here is similar, except we need to unfold twice because the curve goes around. Number 20. Here we need to find prime numbers such that 2020 choose P. When this number is divided by P, the remainder is 9. All right. For this problem, we need to use a general fact. That's if you have a general positive integer n, you choose P, and what is the remainder? Okay. So let me state the general fact, then I'll prove it. So we have this general fact. So n, and we have P, so P is a prime number. Then we have n choose P, this number. When divided by P, the remainder is the same as the integer part when n is divided by P, modulo P. Okay, so this n P is the integer part, or we call floor function, integer part of n over P. So if I write the n as k P plus R is the remainder. So R is between 0 and a P. Then this one is the K, right? So this is the K. Okay, so this is the general fact. Let me prove it. All right, proof. So here I assumed we can write n is just Kp plus R, right? Now n choose P, by definition, this one is n times n minus 1, n minus 2. Okay, so among those all the way to n minus P and plus 1. Now, here we have P numbers, right? P consecutive numbers. One of them is special, that's n minus R, so I put this n minus R here. This one is special because this is multiple P, so it's Kp. And divided by P minus 1 factorial, P factorial. Okay, so here we can cancel P on both sides, right? So we could cancel one P here, and then we multiply P minus 1 factorial on both sides to get rid of the denominator. So from here we get, there are different ways to prove this general fact. What I'm using here is more straightforward. So I have P minus 1 factorial times n choose P equals n times n minus 1, n minus 2, and then to this. Okay, so here is n minus R plus 1, and times this special number, that's the K that is left, right? Okay, we have this is n minus R minus 1 and all the way to n minus P plus 1. Okay, now let's recall, if I have, say I have P consecutive integers, right? Put A plus 1, A plus 2, and all the way to A plus P minus 1. Clearly, if I have P consecutive integers, when they are divided by P, the remainders are just permutation from 0 all the way to P minus 1, right? So the remainders are, when they're divided by P, So when they are divided by p, remainders are just a permutation of 0, 1, 2, all the way to p minus 1, right? All right, so for this particular, for here, if I write here, this number, n minus r, so n minus r, the remainder is 0 when divided by p. So the others are just a permutation of from 1 to p minus 1. So let me put it here. So I get, if I have the n to the n minus 1, all the way to n plus, oops. So it's n minus r plus 1. Yeah, we skip n minus r, so this minus 1, and all the way to n minus p plus 1. It's just a permutation of 1, 2, all the way to p minus 1, right? When divided by p, right? So when divided by p. All right, therefore this implies I have, if I divide by p, the remainder is going to be just k times p minus 1 factorial, right? So it's 1 times 2 times 3 all the way to p minus 1. Of course, here is modular p, right? Modular p. Okay, so if I have, let me summarize this. So I have a k, this is the k, still use the green color. And then we have p minus 1 factorial modular p, right? Modular p. All right, now this tells us these two things, they have the same remainder when divided by p. And this just implies if I take the difference, so p minus 1 factorial, n choose p minus the k times p minus 1 factorial. This is divisible by p, right? They have a common factor, p minus 1 factorial, t minus 1 factorial. So I can pull this one to the front. I'll get a p minus 1 factorial times n choose p minus this k. So this one is divisible by p. Now, p minus 1. So this one is p minus 1 factorial because p is a prime number. So p minus 1 factorial is relatively prime with p. So this one is relatively prime. So, or I say co-prime to p. And if we combine, so we just get n choose p minus k is divisible by p. This is equivalent to saying n choose p have the same remainder as k when divided by tp. By this, we have proved this statement. So let's recall the statement. The statement says if I have one part integer n and a prime number, then this combinatorial number n choose p, combinatorial coefficient n choose p, has the same remainder as the integer part of n divided by p. We say the quotient modular p. The proof is just based on the definition. The only thing we use here is if we have p consecutive integers, if I divide it by p, the remainder is just a permutation from 0 to p minus 1. So here we identify the special one, n minus r. That one is divisible by p, so we're going to 0. So the others is just from 1 to p minus 1 permutation. So we multiply together. This is what we have. Also, we use the fact that p minus 1 factorial because p is prime number. This one is co-prime with the p. So okay, so we can just get rid of it, and this is the proof of the fact. Therefore, our problem is reduced to find the prime number p, so prime number p, such that when 2020 divided by p, the integer part, this one has the remainder 9 when it's divided by p. So this is what we can find. So I can write as another way, I write 2020 equals k times p plus r. So r is between 0 and p. So we want this k, when divided by p, the remainder is 9, right? So that's what we need to find. Okay, we need to identify those prime numbers. We are going to look at two cases. Because when k divided by p is the remaining 9, we can, this just means that k can be written as p times n plus 9. So here n is whole number, 0, 1, 2. Let's look at two cases. Case 1, n is just 0. Let's look at case 1. Case 1, n is 0. For this case, we have the k is simply be 9. So we have 2020 equals 9p plus r, right? Okay, now because r is, since r is between 0 and p, this just means 2020 is bigger or equivalent to 9p, but less than 10 times p, right? We do a simple division, we'll get the p is bigger than 202 and less or equivalent 2020 divided by 9, which if you write as the integer part, that is 2, 2, and 4. Okay, so then we just need to find the prime numbers between the 202 and 224. So we need to find prime numbers between 202 and 224. Well, we can check. There are two such prime numbers. There are two such prime numbers. One is 221, and the other one is 211, and the other one is 223. So for this case, there are two possibilities. Now, let's look at case 2. Case 2. So case 2 is when n is bigger or equal to 1. If n is bigger than 1, that means we have 2020 equals p, okay, let me write one more step. So kp plus r, that equals pn plus p times plus 9 times p plus r. So we have this p squared times n plus 9p plus r. Okay, so in particular, because n is at least 1, so from here we get 2020, this is bigger than p squared. So this implies the p has to be less than 50, right? Obviously, just use relaxed bound. So p is less than 50. And meanwhile, p has to be bigger than, no less than 11. So what we do is we just check. So what we need to do is for this case, because there are not many such numbers between 11 and 50, so we just do case works. So we do case works to find none of them works. Okay, so we just go back to check here. I have from 11, you just look at all the prime numbers between 11 and 50. There are 10 such of 10 prime numbers between 11 and 50. You check one by one, and you find none of them works. Now, you may wonder, wait, but do we have a more efficient way to exclude those things? I would say probably if we do more delicate estimates, try to narrow down the options of P, maybe we can find ways to simplify the calculations. But here, because 2020 is not a big number, so we already have, I think it's manageable, right? You just need to exclude 10 prime numbers, which is not that bad. So I would say for this purpose, this is good enough. All right. So the answer is, if you combine the two cases, case 1 has two cases, has two valid numbers. Case 2, we found that it doesn't work. So if you combine them together, in total, we have two valid prime numbers, satisfy what we want. Okay, this is the end of our 8-week practice. Thanks again for your participation. This has been an unusual experience for all of us.
the most important thing is not how well you have done those exercises. What really matters is that you have been trying, being persistent, and stay to the end. All right, so the summer is over. Have a good fall semester. In particular, please stay safe.